So today we're going to give a overview of an algorithm. I'm not going to go into all the details because it's actually somewhat complicated and would require us to get into a lot of details on how to do multiplication and addition of complex numbers, and that's beyond the scope of this course for the most part. But I'm going to give you a high-level view of this algorithm because it's quite famous and it's one of the most impressive uses of divide and conquer as a strategy to make fast algorithms. It turns out that we can use the fast Fourier transform to multiply integers, n-bit integers, much faster than we've done before. I've been saying that multiplying two n-bit integers takes on the order of n squared time, or we have a slightly faster algorithm that was on the order of n to the log base 2 of 3 time. But it turns out using the FFT, we can get an algorithm that is as fast as O of n to the log n, or O of n log n time. So let's see how this works. It's a really neat trick. So the main technique, the thing we want to solve, is polynomial multiplication. How do we multiply two polynomials? And the trick that we use to multiply polynomials quickly is to actually not represent them in terms of their coefficients, but in terms of the values that they take at certain points. So the FFT is what allows us to very efficiently get from coefficients to values. We're going to need some complex numbers. I won't go into all the details, but you'll see how this technique works. Okay. So imagine we're given two polynomials, let's say a of x and b of x, and they're defined here in terms of their coefficients, right? A of x is some little a naught plus a1 times x plus a2 times x squared plus all the way up to an minus 1 to the x times x to the n minus 1. And similar with b. So just for now, assume that all these coefficients have O of 1 bit, some constant many bits, and also assume that when we're trying to evaluate these polynomials, assume that taking some value x, which has a constant number of bits, and exponentiating that to some power, let's say 5 or n or whatever, takes a constant time. We're not going to worry too much about the details of exponentiation. In the examples that we use, we can assume that the exponentiation can be done very quickly. So let's ask ourselves, what's the running time of just evaluating a of x on some input x? I get some input x and I want to evaluate the polynomial a of x. How long does that take? Similarly, if you're given these two polynomials, a of x and b of x, how fast can you multiply those two polynomials? How quickly can you get c of x, which is just the product of a of x times b of x? So let's look at those two questions now. So typically when we represent polynomials, we represent them in terms of their coefficients, as I said. So here's some little code that helps you compute the value of a polynomial at some point. So here's this function, which is polynomial eval. Don't worry about this; it's just going to print out what the polynomial is. What does it have to do to compute the value of this polynomial at x? Right here are the coefficients of the polynomial. This is going to be 1 plus x, so 2 plus x plus 3x squared plus x cubed. That's what these coefficients mean. And what you have to do is you have to run through the coefficients and the associated exponents for those coefficients, right? This has exponent equal to 0, this is exponent 1, exponent 2, exponent 3, right? And you take the total and you add to the total coefficient times x to the exponent, right? This is just how you would evaluate this polynomial with these coefficients at the point x. So we can run this thing on some example. Here's the coefficients 1, 1, 1. So this polynomial is going to be 1 plus x squared, right? So we're taking this polynomial 1 plus x squared on input 2, and we get value 7 on that, right? So that's because 1 plus x, so 1 plus 2 squared is 4 is 7. That's how we got 7. All right, so okay, so the running time of this was on the order of n if you have an n degree or an n minus 1 degree polynomial. So we had to do a loop through all of the coefficients, right? And we had to do some O of 1 operation. Let's say again that multiplication and exponentiation take constant time, so we had to do this O of 1 operation, but we had to do that O of n times, so the total running time is on the order of n. So we can assume that, roughly speaking, evaluating a polynomial of degree n minus 1 is going to take on the order of n time. Okay, good. What about multiplying two polynomials together? Now, if you think about polynomial multiplication, you have a polynomial with n terms, and you have another polynomial with n terms. You're going to get a new polynomial that has degree, which is if you have an n minus 1 degree polynomial and n minus 1 degree polynomial, you're going to get a polynomial with degree 2n minus 1. If you think about the process of multiplying these polynomials, you're going to have to consider all of the various cross terms and how they combine, right? You're going to have like an x squared term times an x to the fourth term. That's going to give you an x to the sixth term, but you're also going to have an x cubed term times an x cubed term, and right, and that's also going to contribute to the x to the sixth term. Overall, you're going to have to compare all pairs of these polynomials and consider all cross terms. So you'll notice that in this little code that I wrote here, you have to do two for loops. A for loop through for I to get the value of the product of the two polynomials, and then a for loop for j to add up all of the terms for that ith coefficient. And this is just some code that I wrote. You could maybe make this a little bit more efficient, but this naive algorithm is going to run on the order of n squared time. Why n squared? Because if you think about this, you have a polynomial of size roughly n terms, you have a polynomial with roughly n terms, multiply them together, there's going to be n squared terms that have to be multiplied together. So you're going to have to do n squared of these multiplications, right? And you can skip some, but you're still going to be on the order of n squared. So if I try this code on, let's say, an example, here's an example where 1 plus x squared, and this is 2 plus x squared, and I run this code. Okay, so the product of these two polynomials is going to end up being 2 plus 3x squared plus x to the fourth. Okay, and these are the coefficients of the product. But this algorithm that I showed you, this multiplying two polynomials of degree n minus 1, it still took on the order of n squared to compute that. It turns out you can make that faster, and that's what we're going to spend some time doing. We're going to get this down to on the order of n log n. It seems kind of surprising. How could you do this? You have n terms here and n terms here. Don't you have to look at all products? And it turns out you actually don't, and it's very tricky. Okay, so the fast Fourier transform is going to be our method here. It's going to let us get polynomial multiplication down to an algorithm which has on the order of n log n. Let's see how this works. So the main trick is that we have to stop thinking of polynomials in terms of their coefficient representation. Multiplying polynomials when they're in their coefficient representation is not the most efficient. So let's consider another way to represent these polynomials. So here I'm taking a polynomial which is 1 plus 2x minus 3x squared plus x cubed. You guys have all seen how these cubic polynomials look like. I get a cubic polynomial. I'm just plotting it out, and I'm just evaluating a number of points and then plotting that out. Okay, so right now I'm looking at this polynomial a in terms of its coefficients. But notice one thing. There's something very interesting about how you can represent a polynomial. I can also evaluate this polynomial at some arbitrary set of 4 points. It's a cubic polynomial. If I evaluate the polynomial at 4 points, here those 4 points are minus 3, minus 1, 0, and 2. But any arbitrary 4 distinct points, I'm going to plot those 4 points. You can see that the polynomial is taking these values, these y values at these various x's. I just chose these x's somewhat arbitrarily, and now we have these y values that we're plotting. We're showing the x and y values for these 4 points. What you can do is, Python using NumPy has this thing called Polyfit, and what it'll do is it'll let us take any values that a polynomial takes. Let's say in this case we can give it these 4 xy pairs. And it'll try to figure out what was the polynomial that generated those 4 points. And it turns out from here you're going to get a unique polynomial, right? And if you look, we printed out the coefficients of this polynomial. The coefficients are 1, 2, minus 3, and 1, which is exactly the polynomial we started with, right? If you first take the coefficient representation, compute some values of this polynomial at 4 arbitrary points, and these are the arbitrary points, these are the x values, I ended up getting a bunch of xy pairs, and I was able to, just from those red points right there, I was able to fit a polynomial to that, and the polynomial I fit to that was exactly the same polynomial I started with, which is what you'd expect. And it turns out that there's a theorem that says that if you have an n-1 degree polynomial and you evaluate it at n distinct points, the polynomial is uniquely described by its value to those n points, and therefore you can get back the polynomial by just knowing the value of those n points. So you'll notice that I started with n coefficients. When you have an n-1 degree polynomial, you have n coefficients because you have the coefficient for the 0 term and the x to the 0 term, x to the 1 term, all the way up to the x to the n-1 term. If I convert this representation into a value representation, I can now represent the polynomial at n-1 points, and that is again a vector of n minus 1 values, but it gives a unique representation of this polynomial. So again, I have the coefficient representation, which is over here. Here is the coefficient representation, right? There's 4 coefficients, or I can represent it in terms of these 4 values. And I guess I didn't print out the values, but I can do that. Y values, right? So here are these values that I'm using. Okay, good. Why represent polynomials in terms of their values? Okay, so it turns out this is going to make polynomial multiplication much faster. Let's assume that we have polynomial A represented in terms of the values it takes at x0 through xn minus 1, and similarly polynomial B we have represented in terms of the values that it takes at x0 through xn minus 1. Now I want to compute the product of polynomial A times B, right? Let's call that C. What's the product C equals A times B? This is the product of 2 polynomials, but I'm interested in C represented again in the values it takes at these endpoints. It so happens that we can now define C by this vector of values, which is just A of x0 times B of x0, comma, A of x1 times B of x1, comma, dot, 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 A of xn minus 1 times B of xn minus 1. So what you'll notice here is that to compute the C in terms of its value representation, I only needed O of n time. I just had to do O of n multiplications. Assume for now that these multiplications take O of 1 time. So I had to do n minus 1 of these multiplications. That's an O of n time algorithm, which is great. I went from an O of n squared algorithm to an O of n algorithm for multiplying 2 polynomials. But the thing is that I needed these polynomials to be represented in terms of their value representation. How did we choose these points? x0 through xn minus 1, where we evaluated this polynomial. It turns out that any distinct set of endpoints will do in terms of representation. Again, a polynomial is uniquely defined by what values it takes at endpoints. It turns out that we're going to end up choosing the following set of points. You're going to pick some omega, and the points you're going to evaluate the polynomial on are all of the powers of omega. Omega to the 0, omega to the 1, omega squared, omega cubed, all the way up to omega to the n minus 1. So the hard question is, how hard was it to get from the coefficient representation of a polynomial to the value representation of the polynomial? Notice that it takes O of n time to do one polynomial evaluation, where we discussed that earlier. To evaluate the polynomial on just a single point requires O of n time. But we need to evaluate this polynomial on n distinct points to get a value representation. So on total, it takes on the order of n squared, right? We had to do n evaluations, each taking O of n time. The total time is on the order of n squared. That's too bad. Turns out that's actually not so bad. The fast Fourier transform is going to solve this problem for us and make this a lot faster. So let's look at that. Okay, so what does the fast Fourier transform do? It takes in a polynomial in terms of its coefficient representation and some value omega. Right, so here a coefs is just these n minus 1 or n coefficients and some value omega, and it computes a of 1, a of omega squared, all the way up to a of omega to the n minus 1. These are going to be the n distinct points that you're going to evaluate a on, and what it returns is a at these values. Okay, I haven't shown you the algorithm yet. We're going to get to that, but we want an algorithm that runs in time on the order of n log n. So let's just see roughly how this is going to work. So the main trick of the fast Fourier transform is this very neat observation. It's very cute and very simple to see. Notice that, let's consider a in its coefficient form. Once I write a in coefficient form, I have these n coefficients. Assume for simplicity that n is a power of 2, it just makes our life easier. We can take these coefficients and break them up into the even coefficients and the odd coefficients. So I can define this thing called a even, which are just the even coefficients of the polynomial a. So this actually defines a new polynomial. What is that new polynomial? The new polynomial is a0 plus a2 times x plus a4 times x squared, right? This is once I write a even in terms of what it is as a polynomial, this is the polynomial a even. I can similarly take a odd, which are the odd coefficients of this polynomial a, and define this new polynomial. The new polynomial a odd evaluated at x is just going to be a1 plus a3 times x plus a5 times x squared, and so on and so forth, right? The main trick here, and the cutest trick and the thing that makes the fast Fourier transform work is this simple observation. To compute a of x, you can compute the value a of x by simply computing a even on the value x squared plus x times a odd also at the value x squared. If you just think about this expression right here, if you take these two polynomials a even and a odd, if you want to get back to ax, you can do this simple operation. Why is this useful? Why is this so important? Because you'll notice that I took a problem of size n and I broke it into two subproblems of size n over 2. And I'm doing two recursive calls here, but the both two recursive calls have half the size of the original problem. Now, that's very nice. And that's very nice for a number of reasons. You may remember merge sort has a very similar formulation as this. So let's see how this is going to help us. So the fast Fourier transform, I'm going to give you the high-level view of the fast Fourier transform. Here's the pseudocode, but there are some details here that I'm leaving out. The key idea is as follows. First, let's just compute the length of the array. Right, this is your coefficients of the polynomial a that you take in. You break it into the even and the odd coefficients. This is just some nice Pythonic stuff to take the even coefficients of this array, and here you're taking the odd coefficients of the array. You now call FFT. Remember, FFT is supposed to return the value representation of the polynomial a at the points 1 omega all the way up to omega to the n minus 1. Right? What you do is you recursively call FFT on the even coefficients with the input as omega squared. Right? You use the square of omega, and similarly for the odd coefficients. Again with omega squared. So now I have recursively called, I've gotten the a even value representation, the value representation of a even and the value representation of a odd. And now I'm going to use these. How am I going to use these? Well, I now initialize some output array a values, and I can fill it in as follows. I simply use this fact that I used in the previous slide, which is that a values of I is a even values of I. Remember, I got this on omega squared plus omega to the I times a odd values of I. Again, all this line right here, all this is doing is representing this simple fact that I showed you on the previous slide. Right? I'm using this fact right here, and I'm just plugging it in as code right here. This is where we're getting this line of code from. Now, I'm technically cheating here. If you think about what's going on, I shouldn't be able to. This call should return an array of length n over 2 because a even coefs and a odd coefs are of size n over 2. So I shouldn't be able to go all the way up to size n. And it turns out that there is a cheat here, but it so happens that if you choose omega correctly, you can actually fix this very easily. So I'll mention this briefly on the next slide, but I'm going to sort of fudge these details and let you guys look up the stuff in the book because it requires some complex analysis. You have to think about multiplying complex numbers and things like that. So what I'll do is I'll just point out that let's just first consider the running time of this algorithm because that's worthwhile. So notice that here I had to do two recursive calls, but the two recursive calls to FFT were of size n over 2. Right? These are smaller instances of the problem. And then I had to do this O of n operation to compute the final output a values, right? So I end up having a t of n over, if t of n is the running time of this algorithm, I have a t of n over 2 instance, another t of n over 2 instance right here, and this O of n step, this O of n loop right here. Okay, so if you look at t of n equals to 2t of n over 2 plus O of n, we've actually seen that recurrence before. That's the same recurrence for merge sort, and you end up getting a running time of t of n equals O of n log n, which is very cool. What was I sweeping under the rug there? It turns out that to make this algorithm work well and efficiently, you actually need to pick omega to be what's called a complex root of unity. It's defined this way. Omega is going to be this complex number. You'll notice in this complex number, I have the number I here. What is I? That's the square root of -1, right? It's the imaginary number. So we call this an nth root of unity because it turns out if you take omega to the n, you end up getting 1. This is called an nth root of 1. Unity here means 1. Now, I don't want to get into the details of why we chose this particular value for omega, but it turns out it's actually pretty necessary, and if you read the book, you'll get a better sense of this. We did this for 2 reasons. One is that it actually fixes the cheat on the algorithm that I showed you on the previous slide. It actually tells you what to do once you get past the n over 2 value, right? On the previous algorithm, I had to cheat here because you actually can't call a even values of I when I is bigger than n over 2. Same thing with a odd values. It tells you how to fix that, and it turns out you have to just change this to a minus sign once you get past n over 2. So that's cool. And second of all, it actually makes the FFT easy to invert. You notice that we went from coefficients to values? Well, it turns out that once you use this particular omega, you can go from values back to coefficients, and it's a very simple thing. You just simply call FFT on the values of the polynomial, right? But you now use 1 over omega inverse, and you also have to rescale the thing by multiplying by 1 over n, just to fix some scaling issues. But again, you can now go back and forth between the coefficient representation of a polynomial to the value representation of a polynomial. And I suggest you see the book if you want to understand the details of this. To be able to prove this, you do need to do a little bit of work and show that you have what's called an orthogonal matrix, and it's tricky. But I'll let those who are interested to look up the details of that. Let's just finish by noting that right now we have an O of n log n for algorithm for multiplying 2 polynomials. The trick here is simply you have all the details, right? What you do is you start out with 2 polynomials in coefficient form, right? So rather than do the naive multiplication, it takes O of n squared. What we're going to do is convert both of these polynomials using the FFT into value form, right? We just have them represented as values. This is 2 calls to the FFT. We then multiply them together to get C in value form by simply multiplying all of the values together one by one. This is an O of n operation. Now we want to go back and get a coefficient representation of the polynomial C. What do? We simply use this inverse transformation that I said. You can use FFT to both go from coefficients to values, but also to go back from values to coefficients. Now we have C coefficients, and we can return that. Again, we had to do 1 O of n log n call for the FFT, another FFT call, which is on the order of n log n, and then we had to, once we got these, we had to do this O of n call, which multiplies all these terms together, and now we can invert that with another FFT call, which is on the order of n log n. In total, this algorithm has time complexity on the order of n log n. Pretty cool.